In 2018, Microsoft lowered an experimental data center into the ocean off the coast of Scotland. The idea sounded almost futuristic. Instead of using massive air conditioning systems on land, the ocean itself would cool the servers naturally. For years, the project attracted attention from engineers, environmental researchers, and the tech industry. But by 2024, Microsoft quietly ended the program. The company said the experiment had achieved its research goals, but underwater data centers never became part of Microsoft's large-scale AI infrastructure strategy. At first glance, that might have looked like the end of the story. But then, something unexpected happened. In 2026, China officially launched a 24-megawatt underwater data center near Shanghai. The project reportedly cost around $226 million. It was connected to offshore wind power infrastructure and designed to support AI workloads, cloud computing, and large-scale data processing. And suddenly, a strange question emerged. Why would China invest heavily in a technology that one of America's most powerful tech companies had already walked away from? This is not really about cooling. At first, underwater data centers sound like a cooling experiment, a clever engineering trick. Put servers underwater, use ocean temperatures instead of giant cooling systems, reduce electricity consumption. And technically, that is true. According to Chinese state media and project reports, the Shanghai underwater facility may reduce overall power consumption by more than 20% compared to conventional land-based data centers. Its reported power usage effectiveness, or PUE, is below 1.15, an extremely efficient number for a large-scale AI facility. But the deeper you look, the clearer it becomes. This project is probably not just about cooling. Because the AI industry itself is changing for most of the internet era. Software companies mainly competed through algorithms, platforms, and user growth. But modern AI systems operate at an entirely different scale. Training and running large AI models now requires enormous amounts of electricity, cooling capacity, semiconductor hardware, and physical infrastructure. In other words, AI is increasingly becoming an industrial problem, not just a software problem. And this shift is happening globally, across the United States. Major technology companies are already facing growing pressure from electricity demand linked to AI infrastructure. Hyperscale data centers consume enormous amounts of power. GPU clusters generate extreme heat. And in some regions, electrical grids are already struggling to keep up. That changes the entire equation, because in the next phase of the AI race, the winners may not simply be the companies with the smartest models. They may be the ones capable of securing enough energy, cooling, land, and industrial capacity to sustain them. And from that perspective, China's underwater project starts to look very different. Not like an isolated engineering experiment, but like part of a much larger infrastructure strategy. Why Microsoft walked away? To understand why China's underwater project matters, we first need to understand why Microsoft walked away from the idea in the first place. Because Project Natick was not a failure in the traditional sense. Technically, many parts of the experiment actually worked surprisingly well. Microsoft discovered that sealed underwater environments could reduce hardware failure rates. The ocean provided highly stable temperatures, and the company gathered years of valuable operational data. But turning a successful experiment into large-scale infrastructure is a completely different challenge, and that is where the real problems began. The first issue was maintenance. Modern data centers constantly experience hardware failures. A power supply fails, a memory module breaks, a storage device needs replacement on land. Technicians can fix these problems within minutes. Underwater, the situation becomes far more complicated. A sealed module sitting on the ocean floor cannot simply be opened and repaired. In many cases, an entire unit may need to be lifted back to the surface using specialized vessels and heavy equipment. At large scale, that becomes extremely expensive. The second problem was the ocean itself. Salt water is one of the harshest industrial environments on Earth. Corrosion, pressure, biological growth, and long-term material degradation create constant engineering challenges. Over time, marine organisms can accumulate on surfaces and interfere with cooling efficiency. Protecting underwater infrastructure for years at a time requires highly specialized materials, coatings, and maintenance systems. Then there was the infrastructure problem. Supplying electricity, maintaining fiber connections, and operating offshore systems is far more complex than building conventional facilities on land. And for companies like Microsoft, the economics simply may not have made sense, especially when the United States still has enormous amounts of land available for hyperscale data centers. including regions with access to nuclear power, hydroelectricity, and large terrestrial energy grids. From Microsoft's perspective, underwater deployment may have offered interesting engineering advantages, but not enough to justify large-scale commercialization. And that distinction is important because Microsoft was evaluating the technology primarily as a private company focused on efficiency, scalability, and return on investment. China, however, may be evaluating the exact same technology through a very different lens.
Why the same idea makes sense for China?
For Microsoft, underwater infrastructure was ultimately a business decision. For China, it appears to be part of a much broader infrastructure strategy, and that changes the calculation entirely. Unlike private technology companies, governments can justify projects that may not generate immediate financial returns, especially when those projects are tied to energy security, industrial capacity, and long-term technological independence. That context matters because AI systems are becoming dramatically more power-hungry. Training large models now requires enormous amounts of electricity, cooling, and physical compute infrastructure. And China may be approaching this challenge differently from many Western companies. Rather than focusing only on short-term profitability, Beijing appears increasingly focused on building long-term industrial infrastructure around AI. That may help explain why underwater deployment becomes more attractive near coastal hubs like Shanghai. China also possesses several industrial advantages that potentially make these systems easier to scale. It is already the world's largest shipbuilding nation, with extensive experience in offshore engineering, subsea cables, marine materials, and coastal infrastructure. Many of the technical problems involved in underwater data centers, corrosion resistance, offshore power delivery, and subsea maintenance overlap with industries China has already spent years developing. Chinese operators may also be using a different maintenance philosophy. Traditional data centers are designed for constant repair and replacement. Underwater systems, however, may rely more heavily on sealed long-term operation and large-scale redundancy. Instead of repairing individual components, entire modules may simply operate for years before replacement. That approach could reduce maintenance complexity and align more naturally with China's large-scale manufacturing ecosystem. None of this guarantees success, but it does suggest that a technology which made limited economic sense for Microsoft could still become strategically valuable inside a very different industrial system. The real key: energy. But perhaps the most important part of this story is energy, because underneath all the discussions about AI models, chips, and software lies a much simpler reality. AI consumes enormous amounts of electricity. Modern hyperscale AI facilities require massive amounts of continuous power, not only to run GPU clusters, but also to cool them. And as AI systems become larger and more widely deployed, energy is rapidly becoming one of the biggest bottlenecks in the entire industry. This problem is not unique to China. Across the United States, major technology companies are already searching for new energy sources to support future AI growth. Some are investing in nuclear partnerships. Others are building data centers near hydroelectric or renewable energy projects, because in the emerging AI economy, electricity is no longer just an operational cost. It is becoming a strategic resource. And that may explain why Shanghai matters so much. At first glance, placing underwater data centers near one of the most densely populated and expensive cities in the world seems counterintuitive. Why not simply build them farther inland where land is cheaper? Part of the answer may be latency. Modern AI systems increasingly operate in real time. Financial networks, logistics systems, cloud infrastructure, and future autonomous technologies all depend on extremely fast data transmission. Even small delays can become significant at scale. That creates pressure to place compute infrastructure closer to major economic hubs. But Shanghai also faces another challenge: energy constraints. Large coastal megacities already consume enormous amounts of electricity, and hyperscale AI infrastructure places even more pressure on urban grids. This is where offshore infrastructure may change the equation. The Shanghai underwater facility sits near regions with extensive offshore wind development, particularly around Lingang. China has spent years expanding offshore wind capacity along its eastern coastline, and that creates the possibility of linking AI infrastructure more directly to offshore energy production. But offshore wind also introduces another major challenge: stability. Unlike traditional power plants, renewable energy is variable. Wind speeds change, weather conditions fluctuate, and AI infrastructure cannot simply shut down whenever the wind slows. Large-scale AI systems require stable, uninterrupted electricity, which means projects like this only make sense if China believes its broader energy infrastructure is becoming reliable enough to support them. And that may explain why underwater AI facilities are appearing only after years of investment into offshore wind, ultra-high voltage transmission, and national grid expansion. In many ways, this is no longer just an AI story. It is also a story about whether modern energy systems can support the next generation of industrial-scale computing. The geopolitical layer. There is also another layer to this story, geopolitics. Not necessarily in the sense of direct conflict, but in terms of how governments increasingly view AI infrastructure as strategically important. Because modern AI systems are no longer used only for chatbots or consumer applications, advanced computing infrastructure now plays a growing role in logistics, cybersecurity, industrial automation, simulation systems, and potentially military-related research. And as these systems become more important, questions about resilience also become more important. How vulnerable are large AI facilities to disruption? What happens if power systems fail? What happens if critical infrastructure becomes concentrated in a small number of locations? These are questions many governments are likely beginning to consider more seriously. And from that perspective, underwater infrastructure may offer some potential advantages. A conventional hyperscale data center on land is highly visible, centralized, and heavily dependent on surrounding infrastructure. Underwater systems introduce a different security equation. Thermal signatures may become harder to detect, physical access may become more complicated, and disabling offshore infrastructure could potentially require more specialized operations compared to targeting conventional land-based facilities. That does not make underwater systems invulnerable. In fact, they introduce entirely new risks, including subsea cable damage, offshore maintenance challenges, and underwater sabotage concerns. But in a world where infrastructure resilience is becoming increasingly important, some governments may see value in distributing critical systems across multiple environments. And that possibility becomes even more interesting after incidents like the 2022 Nord Stream pipeline sabotage, which demonstrated how strategically important underwater infrastructure can become during periods of geopolitical tension. None of this proves that China is building underwater AI systems specifically for military purposes, but it does suggest that future AI infrastructure may increasingly be designed not only for efficiency, but also for resilience, survivability, and long-term strategic stability. But this is not a perfect solution. But despite all the potential advantages, underwater AI infrastructure still comes with major limitations, and some of them are difficult to solve. The first is environmental risk. Even if underwater systems reduce freshwater usage and improve cooling efficiency, they still generate enormous amounts of heat. That heat has to go somewhere at large scale. Continuously releasing thermal energy into surrounding ocean environments could eventually create ecological concerns, particularly near densely developed coastal regions. Then there is the issue of extreme weather. China's eastern coastline regularly faces powerful typhoons and harsh ocean conditions, even if underwater modules themselves remain protected. Offshore power systems, transmission infrastructure, and subsea connections may still remain vulnerable during severe storms. And there are also security concerns. While underwater infrastructure may reduce visibility in some ways, it can also become more isolated and difficult to monitor continuously. Subsea cables remain vulnerable to accidental damage, anchor strikes, and potentially even sabotage. Protecting underwater infrastructure across large coastal areas is an extremely complex challenge for any country. There is also a broader economic question. Even if projects like this become technically successful, it is still unclear whether they can compete economically with conventional land-based hyperscale facilities over the long term. Especially as other energy strategies continue evolving, including nuclear-powered data centers, advanced cooling systems, and massive inland AI campuses. So, underwater infrastructure may ultimately become only one part of a much larger ecosystem. Not a complete replacement for traditional data centers, and that may be the most important point. This project does not necessarily prove that underwater AI facilities are the future, but it does suggest that countries are beginning to experiment far more aggressively with how AI infrastructure will be powered, protected, and scaled in the decades ahead. So, perhaps the real question is not whether underwater data centers are the future. The more important question may be why China believes they are worth building now. Because this story is ultimately about something much larger than servers under the ocean. It is about energy, infrastructure, industrial capacity, and the growing realization that the future of AI may depend just as much on physical systems as software itself. Whether underwater AI infrastructure succeeds or fails at large scale remains uncertain, but one thing already seems clear. The global AI race is no longer just a competition for smarter algorithms. It is increasingly becoming a competition for power, resilience, and the infrastructure capable of sustaining both.